My name's Liam. I'm a senior cloud engineer here at Octopus Deploy.
Hi everyone, and my name is Frank. I'm a lead engineer at Octopus Deploy. Both Liam and I work in the same team, which is called Modern Deployments. And our focus is to make sure that deploying to Kubernetes is a first-class experience inside Octopus.
Yeah, so today the webinar is focused on how to keep your workloads running reliably in Kubernetes. We're aiming to cater for engineers with entry to mid levels of Kubernetes experience, so you don't need to be a wizard to be able to keep your app running.
So a quick overview of the topics today. First, we'll cover considerations for running multiple replicas or instances of your workload. Then we'll move on to resource requests and limits that'll keep performance predictable. Then we'll talk about scaling up safely, and finally, cover health probes that will help improve the resiliency of your application. So now let's hand it over to Liam to get us started.
The first pillar of reliability: just run more than one. So, why should you run multiple replicas? First, multiple replica setups are really tolerant to failures. You're able to run multiple copies of your workload, and you prevent a single failure causing downtime across your entire application. It also unlocks horizontal scalability. If you need more processing power, instead of paying for ever bigger nodes, you just have multiple smaller ones, being able to target larger or smaller based on your demand. Updating becomes really easy because you can run multiple copies of your app, which means you can update without having an outage. Kubernetes makes the details of scaling up replicas really easy. As you can see on the right, replicas just go from 1 to 2. Now, unfortunately, it's not always as easy as changing your replica count. To successfully scale, you really do need to know your workload. There are two main categories of workloads that run with multiple replicas: stateful and stateless. Stateful apps are what we all think of immediately. It stores persistent data between requests, which can be lost when the application is restarted or replicated. Stateless apps are really easy to replicate. They don't store any persistent data between requests, which means any instance can handle any request. Stateful apps can still run in Kubernetes, but often need design patterns that just work a little bit differently so they can work efficiently. Replicated stateful applications is really out of scope for this talk, but an example of them in use is console or etc.d in Kubernetes, which use Quorum to be able to use many replicas really safely. Other things that you should probably understand is what your workload requires to run. Things like shared file systems or databases. These need to be able to be used efficiently in your environment. Uh, with those workload requirements in mind, let's chat about some of the failure modes that you might get. Broadly, you're going to have two groups: voluntary and involuntary. Voluntary disruptions are generally administrative actions. They update the cluster, you drain a node, and then, you've got an outage now. Uh, you can be preempted by a high priority task, and, there's many things that voluntary disruptions end up being caused by. To be able to manage those, you manage them with pod disruption budgets, generally. They allow you to run updates without worrying whether it'll degrade an application. This is especially important if you've got a platform team that actually wants to update Kubernetes. You can set the pod disruption budget to control how many replicas can be unavailable at a time before voluntary disruptions no longer take effect. When setting up a pod disruption budget, you might consider whether you're running a stateful or stateless application. When you're running a stateless application, you might not care if which ones go down or how many you have in total, but you might just care about having 80% or so of your availability there at a time. Whereas if you're using a quorum-based software or stateful applications, you might want to set it so that the minimum available is the quorum number. Now, involuntary disruptions are where things get dicey. Generally, they're really exceptional circumstances. Kernel panics, the node goes down, the AZ goes down. The only real way to protect against these issues is to have multiple replicas and to spread yourself across multiple failure domains. You can manage this using Affinity, which allows you to control scheduling for your pods and spread over many nodes or pack them all in one node. You can use this, for example, to run a scary pod that runs code for customers over on one node and never run your invoicing, super sensitive, crazy stuff next to it on the same node. Alternatively, if you care more about availability, You can use the topology spread constraint. These allow you to specify a failure domain, usually something like an availability zone, though you can use any label on a node, and lets you scale across those domains, keeping the pods evenly distributed. Now, when you update your workload, replicas are replaced in either a rolling or recreate way. When you use the rolling, it's a default option, and you can tweak it to suit your uptime requirements. You can use a max search to make your replicas go up, or unavailable pods to make some pods get removed prematurely. Keep in mind that pod disruption budgets don't override these options, so just double check the documentation before you depend on them. Alternatively, you can use recreate. All of the pods go down, then the new ones come up. It's not really recommended because it's got downtime, but at the same time, if your application relies on you having a consistent database schema between versions, then you might need to do this. Now I'm going to hand over to Frank, who's going to talk about defining resource requests and limits.
Great, thanks, Liam. Now, most of us probably remember a time when our computer became unresponsive because a single program used up all of the CPU. And the same thing can happen inside a Kubernetes cluster. And this is what we call a noisy neighbor problem, where a workload starts to deprive other workloads of resources. And the way Kubernetes allows us to manage this is via resource requests and limits. So let's look at the screenshot on the right here, which is YAML from a deployment. You can see inside the red square there, we've got the resource request and limit values defined at the container level. And you often see CPU and memory specified. There are also other resource types, but that's beyond the scope of the webinar today. So from this example, you can see that we're requesting 100 millicores of CPU, which is 0.1 of CPU, and with a limit of 1000 millicores. And for memory, we're requesting 70 megs and with a limit of 170 megs. In a nutshell, the request values are used to decide whether a node has enough free capacity to accommodate a pod, whereas the limit are the upper bounds that we set, so Kubernetes can make sure that a pod does not end up affecting other workloads on the node. So let's look at what happens when the limit is reached. In the example here, we've set the limit to for the CPU, we've set the limit to 1000 millicores. So when the container tries to use more of that, it will simply be throttled because CPU time is a compressible resource. It's easy to give the container less of it. But if the container tries to use more memory than the limit of 170, then the container process is terminated. And this usually results in your app being restarted as a replacement is spun up. All right, let's talk about pod scheduling. So from the example, you can see that the requests are defined against the container and not the pod. So what happens is when a new pod is created, the scheduler adds up the request values of all the containers inside the pod and uses that for scheduling. So for example, if I have two containers that request 100 megs each, then the pod's total memory request is 200. The scheduler won't schedule a pod onto a node if the free capacity of the node is less than what's requested. What's interesting here is that the free capacity is determined by the request values of all the pods on the node and not what the pods are actually using. So this means that if you're requesting more than you use consistently, then the nodes will likely be underutilized. Now let's see what happens if you go the other way. On the right here, if you run kubectl describe nodes in your terminal, you'll get a similar output to the screenshot here, where you can see the total request and limits for each resource type on a node. So, for example, in the first row CPU, you can see that we've the pods on this node with the requests are up to 45%, whereas the limit is over 100%. And that means that the node is overcommitted. And often there will be. And this is similar to how internet service providers work, in that they will only buy enough bandwidth to meet the peak demand, rather than the full speed of every customer all downloading at once. So depending on how aggressively you overcommit the nodes, sometimes you will max out the resources and then put the node under pressure. With CPU, because it's a compressible resource, the pods will simply share whatever is available. But when the node is under memory pressure, then it will start evicting pods to free up that memory. There are different ways to adjust which pods get evicted first, but the best thing to do is just to avoid getting into that situation in the first place by setting appropriate requests and limits. So in terms of tuning, we recommend that we start with conservative values, which means higher requests and limits. Then monitor your peak resource usage to see how much slack or buffer you have, and then gradually decrease those values. And at the end of the day, it's about balancing the cost of running the cluster versus the service degradation or disruption that you're willing to accept. Now let's go back to Liam, who will tell you all about scaling up safely.
Thanks, Frank. And just a reminder that we are just listening into the comments. So if you've got any questions, feel free to just plop them in there and we'll answer them as we go. So now that we've got limits in place, how can these be used to react to the changing world that your app lives in? Imagine this. You have a new photo sharing app, and all of a sudden, it's a viral hit. Millions of people are trying to upload their cat photos to your service. Great, right? Lots of money for you. Except you're also probably going to have to figure out how to deal with all those people hitting your service. Responding to this spike can differ based on how your app scales. Your first option is scaling the workload horizontally. This concept calls for additional replicas being created, and that increases your processing capability horizontally. This is done in Kubernetes by using the horizontal pod autoscaler. It's installed by default and scales your workload by increasing the replicas that you've got. You can use CPU, memory, or even custom metrics. It only works for scalable workloads like deployments and stateful sets. Daemon sets that are running on there can't be scaled because they're only ever set to one per node. You've also got vertical scaling. Now, this gives the existing pods that you have more resources. This is done in Kubernetes using the vertical pod autoscaler. It's installed separately and it's available as a plugin in GitHub. It calculates reasonable requests and limits based on the 90th percentile utilization of a pod. You can help limit your growth and contraction based on min allowed and max allowed values. It can either recommend, you can just view the vertical pod autoscaler manifest and you can have a look at what it says is recommended, or it can scale your resources automatically for you. You can do in-place resizing. It is in beta. What that does is it means that your pods scale up without having to restart them. But again, that's not available in most managed Kubernetes environments. It's a kubelet feature flag that you have to enable, and it doesn't usually let you do that in managed service provider kind of details. The new kid on the block is Kata. Kita, I'm not sure how to pronounce it, but the Kubernetes event-driven autoscaler. Previously, you could only really scale based off of the metrics inside the cluster. With Kata, you can respond before there's even a problem. So you can listen to events from external systems. So as an example, you might listen to events from your provider that you use for authentication. And when you've got like a million more signups, you just see that there and you respond to it automatically. You can use these events to scale before the existing pods get overloaded. What this also allows is scaling from zero, similar to a serverless kind of environment, where you can, for example, you have a photo sharing app and you need to compress old images. You can listen to a work queue and only run the pod that compresses these images when there's work to be done. This means that you don't have that compressor running when you don't need it there. Now that you've scaled your workloads, all of a sudden, you're going to need more nodes. That's where cluster scaling comes in. There are two main options. The cluster autoscaler, which is included by default for many managed distributions. This scales based on the presence of pending pods. It uses node groups that you've set up beforehand, and you can set bounds on your scaling so that you don't run into AWS or Azure or GCP limits. Next, you've got Carpenter. Carpenter is built by Kubernetes teams. It's really useful. It's a cost-aware cluster scaler. It automatically selects your machine types dynamically based on the workloads you're running. It provisions based on needs, essentially. For example, if your cluster is all of a sudden using more memory than CPU, it'll attempt to create cluster nodes that fit that profile and try to pack things as tightly as possible. Now, over to Frank, who's talking about implementing health probes.
Great. Thanks, Liam. So as you know, Kubernetes was designed to be fault-tolerant and self-healing, meaning that it will do its best to make sure that incoming requests are processed by healthy instances of your app. But for it to do that, though, Kubernetes needs to know if your app is healthy, and this is where health probes come in. There are 3 types of health probes you can define, and for each one of those, you can customize how long to wait until the probe actually fails, according to your business needs. So let's talk about the first one, the readiness probe. And this tells you whether the app is ready to accept traffic. And when this probe fails, Kubernetes stops sending traffic to your container. Simple. You want this probe to fail fairly quickly so that inbound traffic is not sent to unhealthy instances of your app. Because every request that's sent to an unhealthy instance probably means that you'll get an error back on the client side. Next, we have the liveness probe, and this answers the question, is the app alive, for some definition of alive. And when this probe fails, the container is restarted. And this is to deal with unrecoverable errors that can only be fixed by a restart. And you also want this probe to fail quickly, so replacement can be spun up. And last, we have the startup probe, which tells you whether the app has finished starting up. This is very useful if your app takes a long time to start, since the startup probe will delay the other 2 probes until the startup has succeeded. So by defining a startup probe, you can keep your liveness and readiness probes responding quickly, but not accidentally restart your app during startup. Let's go back to the liveness probe for a bit. In terms of defining what alive means for the liveness probe, I'd like to share one of our learnings within Octopus. So as John mentioned before, in Octopus Cloud, we host the cloud instances inside Kubernetes, and our software relies on an external database to function. A long time ago, the liveness probe included running a query against the database because the app wasn't usable without it. The problem was that sometimes we would see mass restarts of Octopus instances when there were database connectivity issues. And it was then that we realized that if restarting the app wasn't going to help, then we should probably remove the database query from the liveness probe. So if your app depends on an external service to function, but the app can recover by itself once the service is back up, then you probably don't want to include the external service in your liveness probe. Consider putting it in the readiness probe instead. And let's look at how we can go about defining the health probes. It's quite easy. You can either define a custom shell command or look at exposing HTTP, TCP, or gRPC endpoint. Also on the right, we have an example of health probes that are using HTTP endpoints. Under the word liveness probe, you can see the method is HTTP GET, which means that it's a HTTP request, and the path we're pinging is /healthz. The time to fail for a health probe is determined by 2 settings. The first is the period seconds, which means the frequency of the check. And then failure threshold is how many attempts to make before we fail the probe. So in this example here with the liveness probe, it will run once every 10 seconds and fail after the first attempt. With the startup probe, which happens to use the same endpoint, you can see that it fails after 30 attempts. And that gives the app 300 seconds to start. And this is how you can cater for a slow starting app while maintaining quick response for failures once the app is up and running. I'll hand back to Liam to wrap up.
Thanks, Frank. So, in summary, realistically, let Kubernetes do what it's really, really good at, and that's running multiple replicas. It really unlocks Kubernetes functionality and lets you scale horizontally. Using pod disruption budgets then allows you to perform maintenance without worry. Tuning resource requests and limits gives you predictable performance and saves money. You should be able to understand the way your workloads behave under pressure, because that's really important in making your scaling decisions. You should define your appropriate health probes to help your app automatically recover in the case of a failure. And you can use automatic scaling to right-size your workloads. Now, we've got a really good question here from Ranganath Nadella, which I'll show here. So what's the best way to combine a config map and a secret into a single YAML configuration for external application configuration? So what's really interesting here is that config maps, you can mount them as various things. You can mount them as environment variables, or realistically, you'll usually mount a config map as a volume in a Kubernetes pod, which means essentially you're just pulling in that data. But inside the config map, you can do variable substitution with secrets that you pass in as environment variables as well. So for example, what you can have is inside your config map, you pass in a templated variable that gets brought in from your environments from a secret. That allows you to have your secrets be secret and your config map still be templatable. Alternatively, in Octopus deploy, we have variable templating and various other things that you can use to achieve the exact same kind of outcome there. And then how can a merged YAML from a config map and a secret be available as a persistent volume for all pods? So a config map and secret, the only way to really merge these two and make it available as a persistent volume for all pods is to mount it in every single pod manually and to do the same thing over and over and over. If you are running as a replica set or something along those lines, that'll happen automatically because all of the pod configuration is the exact same, regardless of what deployment you're running. So yeah, it's can be tricky, and you'll need to experiment a little bit, but it's definitely possible. Definitely can be done.